Welcome to the lecture. Last time the lecture that I gave went up to measures of location, except that I did not talk about the arithmetic mean. So the uploaded lecture that you have actually goes up to the computation of the median for grouped data. So now I want to proceed with the measures of location, but starting with the arithmetic mean. Now the arithmetic mean. So the arithmetic mean, I'll give the definition. Okay. So let x1, x2 up to xn be data points. These are data points. Okay. So we say the arithmetic mean denoted by x bar, you read this as x bar, is defined x bar is equal to x1 plus x2 plus and so on plus xn divided by n. In short, this can be written as summation of I running from 1 up to n, xi divided by n. So this is the arithmetic mean. Okay? Now, if these data points occur with frequencies as follows, we can define the mean as follows. So I say, if x1, x2 up to xn appear with frequencies f1, f2 up to fn respectively, then the arithmetic mean x bar is defined as x bar is equal to summation I from 1 up to n fi xi divided by summation I running from 1 up to n of fi. So that will be the arithmetic mean once the data appear with frequencies. Having done this, we can now talk about the characteristics of the arithmetic mean. So, characteristics of the arithmetic mean. Okay? One. The first one is as follows. If x1, x2 up to xn are data points with mean x bar, then summation of xi minus x bar is always equal to 0, where I runs from 1. So if you have your data points and from each you subtract the mean and then you add those differences, the answer is always 0. That's the first characteristic of the arithmetic mean. The second one, I'll have to erase this to create space. The second one, 2. Again, we say let x1, x2, up to xn be data points, okay, as we know, with mean. Okay, I don't think that, we just said let them be data points, okay? So we define, or we simply say define di equal to just want to know, should I say xi minus a? Define di equal to this as deviation of xi from any number at all, any number a, then x bar actually is equal to a plus summation di over n. So these are just deviations. These are deviations of xi from a, any number at all. This leads me to the third characteristic of the mean, which is the method of assumed mean. Okay? 3. Assumed mean. Assumed mean. So here, I'll say let xi's I running from 1 up to n. This thing is the same as saying x1, x2 up to xn, but you can choose to write it in this format. Okay? Let these be class marks actually. Class marks, meaning these are the middle value of classes representing grouped data. Okay? These are class marks, these are the middle values of the classes representing grouped data. Okay? Be class marks of a frequency distribution table. Okay? Okay, I'll remind you, this is for grouped data. Okay? Okay? Okay, so we are saying these are class marks of a frequency distribution data where each class is of equal size, is of equal size, say C, okay? So the class size of the classes is equal to C, okay? So we say let A be one of the class marks. Okay? Let A be one of the class marks. So here note, all the values xi's are class marks of the classes in a frequency distribution table. And then we will also clarify that each class has size C. That means all of them have got the same size. Now I'm picking one of the class marks as A. That means that this A is not outside the distribution, like in the other case where A was any number. Then, once this is clear, then we can say define di equal to A minus xi as the deviation of each xi from A. With a bit of manipulation, then as before, we can say then x bar is given as a plus summation di over n. But if I had space here, I could demonstrate that actually di is equal to ui multiplied by c. Okay? So, and if the classes, I'll put on top, and if classes appear with frequencies F1, okay, F1, F2 up to, okay, earlier on I did say up to xn, maybe I should have said xk, but since I used n, I'll still use n. Then our a now, which I wrote, our x bar, which I wrote as a plus summation di over n, or b, x bar equal to a plus c summation fi ui over summation fi. And here ui is equal to 0, comma, plus or negative 1, plus or negative 2, up to whatever value. This method of computing the mean is called the assumed method. Okay? Method of assumed mean. This is about all in terms of the characteristics of the arithmetic mean, but I want to add one or two more. Say, I can say 4. X bar, or the arithmetic mean, in fact let me say, arithmetic mean is very important. It's wrong to say that, but I'll say it. Shouldn't be using that, but it's very important in the sense that all values in the data set are used in its computation. Remember that when we talked about the mode and the median, these are values we're just picking from the data. The mode was the most frequent value in the data set. The median was the middle value of the data set once data are arranged in order of magnitude. So they were just values being picked from the data. But the arithmetic mean, if you look at the formula like I gave you, you can clearly see that all the values in the data set are used in its computation. 5, because of that, it is affected by extreme values. Okay, so that's one disadvantage of the arithmetic mean. When you have very big values in the data set and you compute the mean, they will pull it towards those big values. When you have very small values in the data set, again, the mean will be pulled to the small values. It's a very important disadvantage that you should take note when you are using the arithmetic mean to find a typical value for your data. So you have to really know that the data are well spread. You don't have extreme values in terms of very big or in terms of very small. Having talked about the arithmetic mean, I think this was the last of the measures of central tendencies or measures of location or averages. We move on to what we call measures of spread or measures of dispersion. Dispersion or spread, you can use that, or measures of variance. Measures of dispersion, measures of spread, or measures of variance. This measure of dispersion actually helps us understand how far away data are from the mean. So if you have data that have a very big measure of spread, it's not very good in the sense that most values are far away from the mean. We normally want data to be very near the mean, because the mean is a representative value of the data. So we want most of the data points to be near the mean. Having said that, we have measures of dispersion. These measures help us understand how our data are spread. Here I'll probably talk about 2 or 3, no more. And the first one that I want to talk about is the range. Okay? Range, I'll give the formula already. Range is equal to the maximum value of the data minus the minimum value of the data. So clearly the range gives us how data are spread between the minimum value in the data set and also the maximum value in the data set. So you're simply saying, looking at how the data are spread from the smallest to the largest. So if this value is very big, it's not desirable. You want the spread to be small. Okay? 2, the variance. Variance is the most important measure of spread in statistics. And it is used all the time. And it has no units, so it's very difficult to know whether it's large or small. But from experience, you tend to know when the variance is large and when the variance is small. Definition of the variance is as follows. I'll put it on top here. So, let definition. This is definition of variance. Let x1, x2 up to xn be data, okay, with mean, arithmetic mean, in this case, x bar. Then variance denoted s squared is defined s squared is equal to summation xi minus, minus x bar, the whole thing squared, divided by n minus 1. That is our variance. Of course, our I is running from 1 to n. That is variance. We can manipulate the top, this top here, the top here, this one. We can manipulate it and simplify the variance as follows. So or variance, which is s squared, is equal to summation of xi squared minus summation of xi, everything squared, divided by n and divided by n minus 1. This is a simpler version of variance, and especially if you're using data to compute the variance. Okay? Now, when data occur with frequency, I can remind here, when data occur with frequency, or frequencies if you want, whatever makes sense, then s squared is equal to summation of fxi squared minus summation of fi xi, that divided by summation fi, the whole thing divided by summation fi minus 1. Again, this is just an extension of the above formula, when we have data appearing with frequencies. Okay? Now, having done this, then we want to move on and talk about something very close to variance and has the same interpretation and usage, and you can actually use them interchangeably, and that's the standard deviation. So, standard deviation denoted S by S is the square root of variance, or if you want S squared. Therefore, standard deviation is just equal to, standard deviation is equal to the square root of summation of minus summation f xi squared over summation fi, the whole thing divided by summation fi minus 1. Okay? So this is the standard deviation. The interpretation of standard deviation and standard and variance is the same. They mean the same thing. They can be used interchangeably. They all measure how far away data are from the mean. The last one, we call it the coefficient of variation. The coefficient of variation denoted, okay, I can say coefficient, I don't know whether it's double F there, coefficient of variation, CV, coefficient of variation, is just the standard deviation divided by x bar. Okay, so this is coefficient of variation. Its use is to compare the variance between different samples. So you might have samples which have big variance or standard deviation, and you might think that they are the ones that have more variance. But when you compute coefficient of variation, you realize that in fact the sample that had smaller variance is the one that has more variation. So this is coefficient of variation. Sometimes it's given in percentage form. You can multiply by 100. Okay? Because in a lot of cases, standard deviation is always smaller than the mean. So we are done with the measures of variation. I want now to talk about the data itself. The data, it's in terms of shape. Okay? Now, data distribution. Okay? Say distribution, data distribution, or probability distribution. The first thing I want to talk about is skewness. Skewness is just a measure of symmetry. Okay? Measure of symmetry, or how symmetric the distribution is about the mean. Okay? So, skewness is just a measure of how symmetric data are about the mean, or how symmetric the probability distribution or the data distribution is about the mean. So, we can have skewness, or skewed to the left, okay, or skewed to the right, or symmetric. Data may be symmetric. Okay, symmetric. Now let me talk about skewness to the left, or skewed data that are skewed to the left. Okay? 1. When you have data and you plot against the frequencies and you find that data are distributed like this is skewed to the left. Sometimes we call it negative skew. Negative skewed. Okay, the mean, your mean will be somewhere here, I guess. But you have outliers to the left. So this is a skewed to the left distribution. Then you can have skewed to the right. Your data will look like this when you plot. This is skewed to the right. And, or you can call it positive skewed. Positive skewed. Okay? As positive skewed. When your data are symmetric about the mean, then you have a situation like this. So these data are symmetric about the mean. You can see that when you put a line here, the left-hand side is equal to the right-hand side. You can basically fold this and they will fit perfect. This symmetric data. Symmetric about the mean. Okay? Symmetric about the mean. Now, how do we define, how we calculate skewness? So, definition. Let x1, x2 up to xn be data with mean x bar and standard deviation s. So we have data with x bar as the mean and standard deviation with standard deviation s. Then skewness can be defined as summation I running from 1 to n of xi minus x bar to the power 3 divided by n minus 1 bracket standard deviation to the power 3. So this is the measure of skewness. So if this quantity is negative, then you know your data are negatively skewed. If this quantity is positive, then you know your data are positively skewed. I think if it's 0, we should have a symmetric distribution. If the data occur with frequencies, it's very easy to induce these frequencies in here. If data occur with frequencies, then skewness is equal to summation frequency xi that to power 3 summation fi minus 1 bracket s to the power 3. Okay, that is if data occur with frequencies. Okay, so we've talked about skewness, which measures how symmetric data are about the mean. There is another measure which is called Cartosis. Cartosis is a measure of how peaked the data are. In other words, you want to check how peaked the data are. Some data may look like that, others like that, very highly peaked, others may be flat like this. So Cartosis measures how peaked your data are. So I'll straight away go into the definition. For the data, x1, x2, up to xn with mean x bar and standard deviation. Standard deviation S, Cartosis is equal to summation of xi minus x bar to the power 4 divided by n minus 1 s to the power, multiplied by s to the power 4. So that is Cartosis. It measures how peaked the data are, or how peaked the distribution for your data is. Now, having defined this, and we know there's an important distribution called the normal distribution. Cartosis for the normal distribution, Cartosis for the normal, this we're going to talk about later. Normal distribution is 3. Cartosis for normal distribution is 3. So if we want to define relative cartosis, we simply say relative cartosis is equal to summation xi minus x bar power 4 divided by n minus 1 s to the power 4 minus 3. That is relative cartosis. In other words, we're trying to compare the cartosis of your distribution with that of the normal distribution. If this quantity equals 0, you can conclude that your data have the normal distribution pickedness or bell-shaped. Okay. This ends the first session, where I wanted to complete the measures of location as well as measures of dispersion. In the next session, I'll talk about probability. So we want to talk about probability now, since we've done these measures of dispersion, measures of location, and so on. We move on to probability. Okay. But maybe I should make this the last session of the first unit, so that probability will be another lecture that you can take time to start looking at. Okay, so I'll pause a little here.